This is SpaceTime Series 27, Episode 73, for broadcast on the 17th of June 2024. Coming up on SpaceTime, a new theory of dark matter needed to explain a recently discovered mysterious nearby galaxy. New research dismisses the idea of a lake under the Martian south polar ice cap, and a new daytime optical telescope to study the stars. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have been forced to come up with a new theory of dark matter in order to try to explain a mysterious neighbouring galaxy discovered less than a decade ago. The dwarf galaxy Crater 2 is located approximately 383,000 light-years away, and despite going completely unnoticed until 2016, is actually one of the largest satellite galaxies orbiting the Milky Way. Extremely cold with slow-moving stars, Crater 2 has low surface brightness. And exactly how this galaxy originated remains unclear. A report in the astrophysical journal Letters suggests that its discovery has revealed significant gaps in science's understanding of galaxies, especially those possessing relatively small diameters. It also suggests the possibility that there could be many more undiscovered dwarf galaxies orbiting the Milky Way. We just haven't noticed them yet. Crater 2 is approximately 6,950 light-years wide. That makes it the fourth largest satellite galaxy orbiting the Milky Way. Now, because it's so close, it also has a large angular size, looking like it's twice the size of the full moon. Yet despite its large size, Crater 2 has surprisingly low surface brightness, and that implies it's not very massive. In addition, its velocity dispersion is also low, suggesting that it may have formed in a halo of low dark matter density. Alternatively, it could be the result of tidal interactions with larger galaxies such as the Milky Way and the Large and Small Magellanic Clouds. The trouble is, some simulations suggest that wouldn't explain its relatively large size. Interestingly, its unusually low velocity dispersion is predicted if one uses modified Newtonian dynamics, an alternative to the standard cold dark matter hypothesis. Dark matter makes up 85% of all the matter in the universe, yet scientists have no idea what it really is. It's invisible, but they know it exists because they can see its gravitational influence on normal so-called baryonic matter. That's the stuff that stars, planets, trees, trains, and people are made from. The study's lead author, Haibo Yu from the University of California, Riverside, says that since its discovery, there have been multiple attempts to try and reproduce Crater 2's unusual properties, but that's proven to be very challenging. A satellite galaxy needs to be a smaller galaxy that orbits a larger host galaxy, and dark matter can form a spherical structure under the influence of gravity known as a dark matter halo. Invisible, this halo permeates and surrounds a galaxy like Crater 2. But the very fact that Crater 2 is extremely cold indicates its halo has low density. Hu hypothesizes that Crater 2 evolved in a tidal field of the Milky Way and experienced tidal interactions with a host galaxy, similar to how the Earth's oceans experience tidal forces due to the gravity of the Moon. Now, in theory, these tidal interactions can reduce the density of the dark matter halo. The trouble is, the latest measurements of the orbit of Crater 2 around the Milky Way suggest that the strength of the tidal interactions are simply too weak to lower the satellite galaxy's dark matter density to be consistent with its measurements. Of course, that's assuming that dark matter is made up of cold collisionless particles, as expected from the prevailing cold dark matter theory, SIDM. Another problem is how Crater 2 could have such a large size, as its tidal interactions would tend to reduce its size as the satellite galaxy evolves within the tidal field of the Milky Way. To try and resolve these problems, you and colleagues have looked at different theories to try and explain Crater 2's properties and origins. One of them, called self-interacting dark matter or SIDM, can compellingly explain diverse dark matter distributions. It proposes that dark matter particles self-interact through a dark force, strongly colliding with one another close to the centre of a galaxy. Yu says that his work shows that self-interacting dark matter could explain the unusual properties of Crater 2. He says the key mechanism is that dark matter self-interactions thermalize the halo of Crater 2 and produce a shadow density core, that is, a dark matter density flattened at small radii. By contrast, in a cold dark matter theory halo, the density should increase sharply towards the center of the galaxy. According to you, in self-interacting dark matter, a relatively small strength of tidal interactions, consistent with what one may expect from the measurements of Crater 2's orbit, would be sufficient to lower Crater 2's dark matter density, consistent with the observations. Now, importantly, the galaxy size also expands into a self-interacting dark matter halo, which explains Crater 2's large size. According to this hypothesis, dark matter particles are just more loosely bound in a cold self-interacting dark matter halo than in a, shall we say, more cuspy cold dark matter halo. According to you, the study shows that self-interacting dark matter is better than cold dark matter at explaining how Crater 2 would have originated. This is space-time. Still to come, new research finds the idea of a lake under the Martian South Pole ice cap is now highly unlikely, and a new daytime optical telescope developed to study the stars. All that and more still to come on Space-Time. Claims that a vast pool of liquid water may exist under the Martian South Polar ice cap have taken a bit of a tumble, with new research suggesting it's nothing more than resolution interference between radio waves. The new findings, reported in the journal Science Advances, are a blow to hopes that bright radar reflections seen at the Martian South Pole could be evidence of a subsurface liquid water lake. The findings are based on new computer simulations, which show that small variations in layers of water ice, too subtle for ground-penetrating radar instruments to resolve, could cause constructive interference between radio waves. And this interference could produce reflections whose intensity and variability match observations suggesting that the area contains liquid water. The study's lead author, Daniel Elish from Cornell University, says that while it's still impossible to say that there isn't a liquid water lake down there, the new findings show that there are much simpler ways to get the same observations and readings without having to stretch that far, simply by using mechanisms and materials that we already know exist there. He says just through random chance, you'd wind up creating the same observed signal in the radar. Of course, astronomers already have extensive evidence that liquid water once flowed on the surface of ancient Mars. These include orbital images suggesting that much of the red planet's northern hemisphere was once a gigantic ocean, complete with seashores and sandy beaches. And of course, NASA's Mars Perseverance rover is exploring what was once an ancient river delta in Jezero Crater. Back in 2018, astronomers announced they'd discovered what looked like a lake buried below the Martian South Polar ice cap. The findings were based on an interpretation of radar observations undertaken by ESA's Mars Express orbiter, which can probe below the surface to detect water ice and potentially hidden aquifers. The implications of such a discovery would be enormous. After all, where there's liquid water, there could also be life. However, Lelish says, while the same bright radar reflections would likely indicate a subglacial lake on Earth, the temperature and pressure conditions on Mars are very different. Using simpler models, Lelish had already shown that bright radar signals could be created in the absence of any liquid water. And the new research tells a more complete story, closing gaps in the radar interference hypothesis with more realistic modelling. These findings are based on thousands of randomly generated layering scenarios, which were based only on conditions known to exist at the Martian poles, and then varied the ice layering composition and spacing in ways that would be expected over tens or even hundreds of kilometres. And all those bright adjustments sometimes produce slight subsurface signals consistent with the observations in each of the three frequencies used by the Mars Express orbiter and its Marsus radar instrument. Elish argues that radar waves bouncing off layers spaced too closely for the instrument to resolve wind up being combined, in the process amplifying their peaks and troughs. He says it's the first time scientists have a complete hypothesis that explains the entire population of observed features below the ice cap without having to introduce anything unique or odd. In other words, Occam's razor. The result, he says, is that you wind up getting bright reflections scattered all over the place, which is exactly what you'd expect to find from thin-layer interference in radar. While not ruling out the possibility for some potential future detection by some more capable instruments, Lalish says he suspects the story of liquid water and its potential for life on the red planet sadly ended long ago. This is Space-Time. Still to come, astronomers pioneer a new technique for observing celestial objects during daytime, potentially allowing round-the-clock visual monitoring of stars and satellites. And later in the Science Report, a new approach to night vision technology using an infrared filter thinner than a piece of cling wrap. All that and more still to come on Space-Time. Astronomers have pioneered a new technique for observing celestial objects during the day, potentially allowing round-the-clock visual monitoring of stars and satellites. The key is a unique new type of optical telescope, which its builders are calling the Huntsman. The new instrument, constructed at the Siding Spring Observatory in the far west of New South Wales, comprises an array of 10 camera lenses, originally designed for ultra-sensitive night sky observations, but which it turns out can accurately measure stars, satellites and other targets, even when the sun's high overhead. A report in the Journal of the Publications of the Astronomical Society of Australia shows that researchers have been using special broadband filters on the test version of the telescope to block out most of the daylight while allowing specific wavelengths from celestial objects to pass on through. The study's lead author, Sarah Caddy from Macquarie University, says people have been trying to observe stars and satellites in optical wavelengths during the day for centuries, but it's always been very difficult to do. However, she says tests showed that the new Huntsman telescope can achieve remarkable results even during daylight hours. And that's important because the Huntsman's daytime capabilities allows continual monitoring of bright stars like the red supergiant Betelgeuse, which can be unobservable at night for months at a time when it's positioned close to or behind the sun. And monitoring Betelgeuse is important. You see, if you recall, it dimmed substantially in late 2019 through to 2020, likely due to a major ejection of gas and dust. Astronomers know Betelgeuse is reaching the end of its life. It'll blow up soon. Now, soon, in astronomical terms, could mean in 1 million years from now. Of course, it could also mean tomorrow. For about 4 months of the year, Betelgeuse is only observable during daylight hours because the sun gets between it and the Earth. Associate Professor Lee Spittler, who's head of space projects at Macquarie's Australian Astronomical Optics, says that without this daytime mode, astronomers would have no idea if one of the brightest stars in the sky has gone supernova until a few months after its explosive light reached the Earth. And it's not just stars and other celestial objects. The new telescope would also have significance in the rapidly expanding field of space situational awareness. That is the close monitoring of the ever-growing population of satellites, space debris, and other artificial objects orbiting the Earth. With plans to launch a further at least 50,000 low-Earth satellites in the next decade, there's a pressing need for dedicated day- and nighttime telescope networks which are continually detecting and tracking satellites and visually checking their composition, age, and condition. Opening up to daytime observation of satellites would allow scientists to monitor not just where they are, but also their orientation. And that adds to the information gathered from radar and other monitoring methods, thereby adding to the protection against potential collisions. Spittler says being able to do accurate round-the-clock observations shatters long-standing restrictions on when astronomers can scan the heavens.
The Huntsman telescope is a kind of really unique telescope that exists in New South Wales. The main thing that's special about it, it uses Canon telephoto lenses to take images of distant galaxies and stars.
That sort of thing's been done before, but this is also using filters to be able to carry out those observations in the daylight.
Yeah, that's right. So the idea is kind of inspired by a really neat telescope called Dragonfly, which is in North America. But the Huntsman telescope kind of has a view of the southern skies, and we've upgraded it to actually have filter wheels, which means that we can select the wavelength of light that we observe. Otherwise, like before we upgraded it, we'd have to physically drive out to the telescope, change the filters, change the wavelength to do a different science case. But right now, with the click of a button, we can actually change everything, the setup, even though we're 7 hours drive away from it right now.
Yeah, now Macquarie University is in Sydney, and the telescope's located at the Siding Spring Observatory out in the far west of New South Wales. So it's a pleasant but long drive.
That's right, yeah. Yeah, we worked pretty hard to try to automate the Huntsman telescope so that it can run itself, open itself when the weather's clear, take some data, shut itself down, and the data is then transferred to Sydney, where we have some servers and we can work on the data over here.
And what's the advantage of being able to use the same telescope for both day and nighttime observations?
Yeah, so what we started to realize with the Canon lenses that we use is that we can actually start seeing stars during the daytime. What this means in practice is that the facility, which otherwise was just completely shut down during the daytime, can be kind of twice as productive if you can find a useful science case during the daytime. And so that's what we've been pursuing for the last few years, trying to figure out ways to do useful astronomy during the daytime.
And what sort of arguments are you putting up for that? I've noticed you've mentioned Betelgeuse as some call it.
Yeah, so the one that really latched onto is that the stars that are kind of near the equator, if you look up into the sky, for months of the year, those stars actually get so close to the sun because the Earth is moving around the sun and stars kind of go onto the other side of the sun. So for that few months period, you just can't see certain stars during the nighttime. And so traditionally, astronomers would just not observe them, which is fine because most stars that you could see during the daytime aren't doing anything so interesting. So you could just wait a month or two and they're kind of the same brightness, nothing's much changed. But the story is very different for stars that are rapidly changing. So a great example is Betelgeuse. It's in the final phases of its life. It's a red giant star. And so what astronomers have realized is that it's kind of going through the final stages, and therefore it's undergoing pretty, not rapid, but like day to day, week to week, it is changing in brightness. So that's a clue that something astrophysically interesting is happening to it. And the trouble with Betelgeuse is that it gets close to the sun. And so if you kind of look at the historical records of how bright Betelgeuse was, there's just big gaps every single year, kind of this time of year, where it's just too close to the sun to see at nighttime. And so astronomers just have had no idea what's happening to Betelgeuse.
Yeah, Betelgeuse is one of those stars which could go supernova any day now. It could happen tomorrow or it could happen a million years from now, but it's going to happen. And it's certainly something astronomers want to see so they can watch the step-by-step process of a red supergiant undergoing a core collapse supernova event. It's going to answer a lot of questions, and it's nearby too. Luckily, it's not pointing in our direction, but it'll be a spectacular. It'll be as bright in the daylight as maybe it'll become, I guess, the second brightest object in the daytime sky.
That's right. Yeah, it's super exciting. If Betelgeuse goes supernova and we can see it in our lifetime, it would be one of the most important astronomy events that will have occurred because, literally people can see it during the daytime. It will be spectacular. The last time something went supernova in kind of, modern astronomy history, it was, in the 80s. And astronomers still...
I remember it well.
Yeah, you do. Yeah. Well, astronomers still study that because it's such an interesting and rare occurrence. Even though it's in another galaxy, it tells you so much about the astrophysics of the final phases of the life of a star. And so they still study it today. And so you can imagine that Betelgeuse is literally going supernova right now, or the light from that event is happening right now. And without this capability, we just wouldn't have we wouldn't even know for a few months' time until it became nighttime again when we could observe Betelgeuse.
Yeah, I think there are still astronomers kicking themselves that they didn't look at their data early enough when 1987A exploded.
Yeah, that's right. In that game of hunting for supernovas, you got to get there kind of before it happens. That's the ideal thing because there's kind of this breakout phase where the brightness is increasing very rapidly, and that's really where some interesting astrophysics can be had because you're literally watching a star explode, and so how it propagates outward, and you learn a lot of information from the brightness of that star as it increases in brightness.
Luckily, thanks to 1987A, we now know that the early warning signs are actually neutrinos. So if we look for neutrinos first with IceCube and places like that, then that should give us a warning. Look in this direction now. And if it happens to be daytime, that's where Huntsman will come in.
Exactly. I hadn't thought about reaching out to them to tell us if they have a neutrino burst in a particular direction. Maybe we can point the telescope during the daytime and try to catch something.
Indeed. Now, it's not just astronomical objects either, is it? You're you're also looking at monitoring satellite movements as well.
That's right. So this work is really led by my PhD student, Sarah Caddy. She's really taken the idea and run with it. So we have a paper out now that's about the daytime Betelgeuse monitoring, but she's now currently wrapping up another paper where we're focusing on looking at satellites that pass overhead Sydney and trying to understand how well you can actually detect them. And I don't want to reveal the results from that work because it's still to come out, but it's pretty exciting because it's relatively easy to see them during the daytime if you know where to look using the current telescope setup that we have now.
I thought the big problem was not seeing them.
Yeah, these days it's really easy to see them during twilight. They're just kind of zipping around. We are focusing on the Starlink satellites in particular. They're the most prolific. There's a kind of mega constellation up there. From a observing astronomy perspective, they're kind of annoying because we have a big bright streak passing overhead. On the other hand, if you're trying to understand how to observe satellites from the ground, which is immense value from a space traffic management perspective. And Starlink satellites are actually really useful from a scientific perspective because they're kind of a control sample. They're not all the same, but a lot of them are the same. And so by using them as a test case, you can start to understand how the brightness, if you track it across the sky, changes. It tells you about the orientation of the satellite relative to the sun and the observer. So they're really useful as a science use case, a control sample, essentially.
Can you use them to study the upper atmosphere as well?
Hadn't thought about that. Do you mean kind of like absorbing the...
I mean physically the changes in their orbital paths as a result of intercepting more atmosphere because of things like the solar wind and coronal mass ejections and things like that.
Yeah, definitely. We haven't particularly explored that use case exactly, but you're right. One of the main challenges with even practically observing them is that it's kind of hard to know where they are exactly. There's ways to observe where they are. They use radar and things like that. But even if you kind of have an accurate observation, one orbit later, so like 90 minutes later when it passes overhead again, the atmospheric drag, even though it's kind of in space, there's still some air up there. And what that does is it slowly changes the orbit. It kind of puffs it out or brings it closer to the Earth. And so you are always accumulating you're always moving. The orbit isn't perfectly circular by any means. It's always changing.
This will let you study that, I guess.
That's right. Yeah, I guess eventually there's a few things that we can use this for. One is just to understand the orientation of satellites. So if a satellite, for example, is tumbling out of control, it's pretty clear to see that when you look at the data that we're collecting because the brightness changes kind of periodically. You can imagine big solar panels that are kind of facing the right angle to reflect light from the sun onto the observatory, the telescope, and you might just see that kind of periodically changing. And so I think one use case is to understand what's happening to a satellite. Is it starting to tumble? Is it moving to the wrong location? As well as kind of identifying things. So most of the time you know what satellite you're looking at, but there are use cases where all of a sudden a new object appears there and you want to kind of fingerprint it. And one way to do that is to just monitor it as it streaks across the sky and look for how it changes across the sky. And that gives you some clues to what's it made of, how large the solar panels are, and things like that.
With Huntsman, is it you've got these 10 individual lenses? Are they all sending their light to a single photoreceptor plate, or is it 10 separate plates that act interferometer?
Yeah, no, we're not doing interferometry. So the cameras that sit behind each of the 10 lenses, they operate independently.
Right.
They capture data of, in this case, right now, the current configuration is the same patch of sky. We're trying to kind of increase the amount of light that you gather effectively from a target. With one Canon lens, you can kind of see only so much, but with 10 of them, you kind of have a few factors better sensitivity, and so you can see fainter objects by, after the fact, kind of adding the data that you collect.
Layering on top of each other to improve the light intensity.
That's right. Or otherwise, you can use those filters that we talked about earlier to choose different wavelengths of light. So a good example is for that satellite use case, you can observe it at red, blue, and green light at the same time, which is pretty unique. A lot of telescopes just have a single telescope, a single wavelength of light at a time. But with the 10 lenses, we can actually configure it to, 3 of them doing one color, the other 3 doing another color, to really maximize the information that you get at any one time.
And by looking at different wavelengths, you get to understand different characteristics of the target.
That's right. When you look at stars, for example, it tells you about the emission. So if you have really hot star, it will tend to be blue. And so by looking at the different colors of light, you can say that the stuff that's coming out of, Betelgeuse's explosion is just really hot gas. It's coming out. For satellites, it's more like you typically see the solar panels, like sunlight hitting a solar panel. It reflects down to Earth. Now, solar panels are by design will absorb most of that light coming in from the sun, but the stuff that they don't absorb actually tells you potentially about the materials that are in that solar panel, the particular elements that are used for that solar panel. And so you can kind of reverse engineer what a solar panel is made of, or if it's starting to degrade. So micrometeorites are up there, are kind of peppering these solar panels and the spacecraft. And so over time, if you were to monitor a satellite, you might actually see a change in the color that we could detect that would allow you to understand, is the satellite changing? Is the solar panels broken? Has something happened to it?
It's a good monitoring tool for satellite operators as well.
I believe so, yeah. I guess we're kind of just astronomers trying to work with pushing the boundary of what we can do with the telescope technology. So we're really kind of looking to chat with people that work in this area and learn what the problems that they have, work with industry partners potentially to see how we can help them out so that they can better manage their assets, understand how things are changing up there.
Normally with any telescope, it's a question of using mirrors, but you're using a different system with the Canon lenses. Why?
Yeah, so one thing about mirror-based telescopes that astronomers normally use is they're great because you make them huge. We're talking about 30-meter telescopes in the near future. And you can do it because you can make a big mirror or a segmented mirror. The trouble with mirrors is that they're not perfect. They're not perfectly smooth. And normally when you have a mirror, you have other mirrors or lenses that are kind of in the optical path, which means basically light from a target has to pass by structures and other cameras and things like that. And that modifies the light from the target in a way that is not, it kind of takes away from some certain science cases. And so a refractive system that we use with Huntsman actually allows us to mitigate some of that effect so that we see less of the telescope that we're looking through in the actual data. And that makes it a lot easier to get to the pristine information that we're trying to get at. For daytime observing, it's particularly important because when you have a bright, big source of light like the sun nearby, refractive system can better handle that. Basically, because the telephoto lenses are used on Earth by photographers mostly to take images of sports and wildlife photography. And you can imagine if someone's trying to take a picture of like a lion or something like that, and there's a beautiful sunset in the background, they want to minimize things like lens flare and stuff like that. And so we're kind of taking advantage of that refractive system, the really high quality lenses, in order to reduce the impact of the sun during the daytime so that we can see the target that we're interested in and ideally nothing else.
That's Associate Professor Lee Spitler, Head of Space Projects at Macquarie University's Australian Astronomical Optics. And this is Space Time. And time now for a brief look at some of the other stories making news in science this week with the Science Report. A new study warns that internet addiction in teens could be changing the way their brains work. A report in the journal PLOS Mental Health reviewed 12 studies looking at the brain activity of teenagers with internet addiction in order to see if there were any differences in connectivity between brain regions. They found that in all the studies they selected, internet-addicted teens showed evidence of disruption in their brain function when performing activities that required attention, planning, decision-making, and controlling impulsivity. The authors admit there's a lot more research that still needs to be done in order to paint a full picture of the impact of internet usage. But it appears that internet addiction could be changing teenage behavior during what is an important stage of their development. Scientists have made significant progress in their journey to deliver a new approach to night vision technology by creating an infrared filter that's thinner than a piece of cling wrap. A report in the journal Advanced Materials claims the work's demonstrated enhanced infrared vision nonlinear upconversion technology using a non-local lithium niobate metasurface. The work by the Australian Research Council's Centre for Excellence for Transformative Meta-Optical Systems could one day be placed on everyday eyewear, allowing the user to view the infrared and visible light spectrums at the same time. Scientists have reined in the timing of the domestication of the modern horse to around 2700 BCE. The findings, reported in the journal Nature, are based on DNA analysis of 475 ancient and 77 modern horses, finding that at around 2200 BCE, there was a distinct change in horse breeding practices, which led to the replacement of nearly all horse lineages with modern domestic bloodlines. They also found that around 2700 BCE, the age at which horses reproduced suddenly reduced, and that facilitated the breeding of new domestic horses. The authors say their findings bring forward the date of the domestication of the modern horse by at least 300 years from the previously accepted time period of 3000 BCE. Loch Ness monster hunters are now pleading with NASA to help them in their ongoing quest to find the ever-elusive beastie. People have been looking for Nessie ever since sightings of the legendary cryptid caught media attention back in the 1930s. Despite environmental DNA studies showing a distinct lack of anything that could possibly be described as plesiosaur DNA, Nessie hunters insist there are just too many sightings of the Loch Ness monster for there to be nothing to it. Tim Mendham from Australian Skeptics says a local tour group, the Loch Ness Centre, has asked for the American Space Agency's expertise to help them in their search.
I love Loch Ness. I love Nessie. I've been to Loch Ness 3 times, I must admit. I've been to the museum there 3 times. It's changed over the years. Lovely place, highly recommended, but I haven't seen the Loch Ness monster. Obviously, that's the one reason why a lot of people go to Loch Ness is to see a monster.
But there have been over 1,150 sightings.
That's reported sightings. But basically, evidence is the hard bit. A lot of sightings, which a lot of the sightings have been shown to be sort of, and a lot of them are just so vague you can't really investigate them. Some of the investigators are saying, can NASA help us with their advanced imaging technology? But they don't exactly say exactly what and how. But they've suggested you can scan the loch and find things in there. I'm sure you would find things in there. It's a pretty murky sort of... Actually, apparently not always murky.
They've scanned the loch already. They've done that heaps of times.
They've done it, but not from space.
Right. Good point.
They have done it with boats travelling up and down and submarines and all sorts of things, but not from space.
And they've done DNA tests of the environment there. They've not found any Nessie DNA. It's mainly eels, things like that, things that really do exist.
Again, Nessie is a problem because there's only one Nessie. How long does Nessie live? If there's only one, it can't breed, so therefore there's not a population there. If there's a population, which you need to continue the species being there, you need more than one, you need more than two, you need a family of them, and it could be a very large family.
Maybe they're like salmon and they live in the sea and then they only come into the loch to breed.
No, there is no direct link. Okay, there is the Ness River, or the River Ness, which runs, I think, from the top of the loch towards the sea, but you can't actually...
There are lochs there, aren't there?
There's all sorts of things, and there's no underwater cave. Anyway, they are saying they're going to try and reach the people at NASA. They're going to get Nessie hunters to all work together and reach the NASA through social media. I don't know what that means. They're going to email them. They're going to put up things on X and other sort of Twitter-type things. They're going to put TikTok things up, and obviously that will convince NASA to say, yes, we'll join you.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.